we continue the discussion on integer programming. So, we take this example, and the first rule in solving any integer programming problem is to relax the integer restriction, treat it as a linear programming problem and solve it. If it turns out that the LP optimum is integer valued, then it is also optimum to the IP. So, we try solving this problem by relaxing the integer restriction, making it a linear programming problem, and we get this. So, the optimum solution to the corresponding LP is x1 equal to 28 by 9, x2 equal to 133 by 45, z equal to 273 by 45. Now, both x1 and x2 have non-integer value or fractional value. We can take any one of them for further consideration, and we choose that variable which has the largest fractional coefficient as a general consistent guideline. So, we take variable x2 and write the constraint corresponding to the basic variable x2, which is the second constraint, from the simplex table, and we get x2 plus 4 by 15 x3 plus 7 by 45 x4 equals 133 by 45. Now, this equation is rewritten in a certain form, wherein the right hand side value, because this is an optimal simplex table or an optimal table in a simplex iteration, this right hand side should always be non-negative. So, this is written as an integer plus a fractional value less than 1. So, this becomes 2 plus 43 by 45. Left hand side, the value, the coefficients are again written in the same form, an integer plus a positive fractional value. In this case, it turns out x2 is an integer, so x2 remains. 4 by 15 has a fractional value which is positive, which is less than 1. So, it is straight away written as 4 by 15 x3. For example, if this had been say 24 by 15, then we would write it as 1 plus 9 by 15, x3 plus 9 by 15 x3. This again becomes 7 by 45 x4. For example, if it had been say minus 7 by 45, then we would write it as minus x4 plus 38 by 45 x4. So, it should always be written as an integer plus a positive coefficient less than 1. The integer could be negative. If the coefficient itself is negative, then the corresponding integer will be negative, but you will have a positive coefficient less than 1. So, we have written this. Now, we try to match the integer part on the left hand side and the fraction part, integer part on the left hand side with the integer part on the right hand side, and the fractional part on the left hand side with the fractional part on the right hand side. So, this is the only integer part, this is matched against this. This whole thing is to be matched against this. Now, we know that this part of the equation has strictly positive coefficients for each of these variables. So, this is clearly a positive term. The right hand side has a fractional portion which is also a positive term. So, from this we can write an inequality which looks like this: 4 by 15 x3 plus 7 by 45 x4 is greater than or equal to 43 by 45. The greater than or equal to comes because we know this is an integer, this is an integer, and this is an equation. So, the fractional portion will have to match. So, 4 by 15 x3 plus 7 by 45 x4 will have a fractional portion which has to be 43 by 45, but this is a positive quantity. So, this could be simply 43 by 45 or 1 and 43 by 45 or 2 and 43 by 45 and so on. Therefore, we make a general assumption here, we do not restrict it to an equation, we make it an inequality. If we make it to an equation, there can be a situation where we could be wrong, but then you make it an inequality, you are always right. So, you make this constraint from an existing equation. Now, this is called a cut, and this is called a Gomori cut based on Ralph Gomori, whose algorithm we are right now seeing. It is called a Gomori cut, and then we rewrite the cut. Now the cut is written as 4 by 15 x3 plus 7 by 45 x4 minus x5 equal to 43 by 45, from which x5 minus 4 by 15 x3 minus 7 by 45 x4 equal to minus 43 by 45. Multiply this whole thing with a minus 1 to get minus 4 by 15 x3 minus 7 by 45 x4 plus x5 equal to minus 43 by 45. Now write it exactly here with x5 as a basic variable. So create another row with x5 as basic variable. So this becomes 0x1 plus 0x2 minus 4 by 15 x3 minus 7 by 45 x4 plus x5 equal to minus 43 by 45. Introduce an x5 again into the problem. So a Gomori cut introduces an additional constraint and also introduces an additional variable. Now the additional variable is always a negative slack variable, because a Gomori cut is always a greater than or equal to cut. So you will get a negative slack, and the negative slack will come into the basis. It will come into the basis because you multiply the whole thing with a minus 1, and because the negative slack comes into the basis, it comes into the basis with a plus 1 coefficient, the effect being the right hand side being negative. So the current solution will be infeasible. In all Gomori cuts, the current solution will be infeasible. You will be adding a new constraint, and the very fact that you should have a negative here, it indicates you are doing it all right. So now introducing variable x5, x5 has 0, 0, 1 that come here, x5 becomes a basic variable with 0. And because this is a basic variable with 0, and in the Gomori cut you always write the new variable in terms of existing non-basic variables, like what we have done, because you take it from an equation in a simplex table. So any equation in a simplex table represents a basic variable in terms of the non-basic variables, and because we do it that way and we put this x5 in, you will the Cj minus Zj will not be affected by the addition of the new variable, because this has a coefficient of 0. The values come only against the non-basic variables, the coefficient in the objective function is 0, so Cj minus Zj is not affected. Right, you do not even have to worry, just because it is a slack, negative slack with a contribution of 0, Cj minus Zj is not affected. So optimality condition does not change, feasibility is affected. So you go ahead and do a dual simplex iteration on this. So do a dual simplex iteration by pushing this out and calculate a theta. Right now you have to calculate a theta, let us do that, since we are doing it first time, let us do that. So calculate a theta. Remember that theta should always be, this is a maximization problem, so minimum theta straight away comes, and in a dual simplex iteration pivot has to be a negative number. So 9 by 15 divided by 4 by 15 is 9 by 4 and 4 by 7, so this enters and this is your pivot. So now go back and do one more iteration here, yes. Nine by 4. Oh, I am sorry, I forgot to multiply by 3. So this is 12 by 7, and it's still smaller. So 12 by 7 enters. So 12 by 7 enters. So you have x1, x2, and you have x4, and do a straightforward iteration. So the contribution will be 1, 1, so 1, 1 and 0. Let me just write down the next table here just to save time. So you will get 1, 0, 1 by 7, 0, 5 by 7, 17 by 7, 0 1 0 0 1 2, and x4 has 0 0 12 by 7 1 minus 45 by 7 43 by 7, and this will be 0 0 minus 1 by 7 0 minus 12 by 7 31 by 7. So, this is the table after one iteration that we have.
Is the same as we got x2 less than equal to 2, so because the constraint is the same.
Yeah, it happens in this case, but later you will see that you need not get the same thing in the branch and bound as well as in the Gomori. It can be different. We will see a little later after we complete it. The question was the fact that x2 has become equal to 2, does the Gomori, this question, implied question is, does this reduce to x2 less than or equal to 2, in which case we did exactly that in the branch and bound. So, are we doing the same thing? The answer is, later we will see that this actually reduces to x2 less than or equal to 2, and we will verify that. Now, whether it implies x2 the same constraint or whatever, the Gomori cut will not and need not be the same as the branch and bound cut. You will realize later once we see in the branch and bound algorithm, at every stage or at every node, the cut is always an upper bound or a lower bound on the variable. You will always get cuts of the form xk less than or equal to some lk or greater than or equal to lk or xk less than or equal to uk. In a Gomori cut, you could have a general constraint. This can reduce to, for example, some 3x1 plus 2x2 less than or equal to constant. It could reduce to something like that. Right. Now, from this solution we again observe that the three basic variables, please remember the way we have created, the way this problem is written, it is also a very general assumption that integer programming problems will have, it is assumed that if the right hand sides are integers, then the slack variables are also bound to be integers. Otherwise, you are in a slightly different spot. For example, you may have a situation where decision variables are integers and slack variables need not be. You may get into that situation, but in general terminology, when you say something as an all integer algorithm, it implies that decision variables are integers, right hand sides are integers, which means slack variables are also integers. So, decision variables and slack variables are integers. Now, what happens to the slack variable corresponding to the Gomori cut? The slack variable corresponding to the Gomori cut should also be an integer, because this is the governing constraint from which this equation is written. And when you match the left hand sides and the right hand sides, you know that this quantity is either 43 by 45 or 43 by 45 plus an integer. It cannot be anything else. Therefore, this x5 that comes in, the minus x5 that comes in here, which becomes plus x5 after you multiply with a minus 1, should also become an integer greater than or equal to 0. So, you will have all your variables, slack variables, original slack variables in the problem, plus every slack variable corresponding to every Gomori cut will be greater than or equal to 0 and integer. So, we assume the moment we say we are solving an all integer problem, we are assuming all that. Now, go back, you realize x1 and x4, which are meant to be integers, are now having fractional values. Please remember that at the optimum, all the basic variables will have to be integers. Non-basic variables are at 0, so we do not worry about them, they are having an integer value, but all basic variables have to be integers. For example, it may not occur, but if it happened in this iteration that x1 is 2 and x4 has a fraction, or if we had x1, x4 and x3, with x4 and x3 having fractional values and x2 having an integer value, we have still not reached the optimum. At the optimum, all basic variables will have to take integer values. So, we look at these two and then find out the variable that has once again the largest fractional coefficient and generate another Gomori cut.
The RHS is an integer, then x3, x4 will not be fractional.
Yeah, understood. The point I was trying to convey is the message that if you are looking at an all integer problem, then you will have, I mean, thinking along with the problem, the statement is right, because x3 and x4 are slack variables that come in only one constraint.
They are going to once.
Absolutely. So it's right, but then the point I was trying to convey is it is absolutely necessary that all basic variables have to be integers. So you take x4 which is here, and then write the corresponding x1 is 17 by 7, this is 1 by 7, this is 3 by 7. So we will take this. This would help us in understanding something, but it will still be consistent in taking this. If you have taken this, then you have a minus term here. So when you write the Gomori cut, this will become minus 1 or minus 7 plus something. This would become something else. So we will still go by x1 and write x1 plus 1 by 7 x3 plus 5 by 7 x5 equal to 17 by 7. So this simply becomes x1 plus 1 by 7 x3 plus 5 by 7 x5 is equal to 2 plus 3 by 7, from which the Gomori cut will be 1 by 7 x3 plus 5 by 7 x5 is greater than or equal to 3 by 7, which would give us minus 1 by 7 x3 minus 5 by 7 x5 plus x6 equal to minus 3 by 7. So this will be the Gomori cut corresponding to this solution. So we have to write this again. So here I need to create some more things here. So you need to create it a little carefully, and very typically just introducing an x6 here. So x6 gets 0 0 0 1, I have an x6 here with a 0 here, 0 or minus 1 by 7 x3, 0 0 minus 1 by 7 0 minus 5 by 7 1, you get 17 by 7, and what do you have here, 2 43 by 7 minus 3 by 7, this is okay, I have not written the Cj minus Zj, okay, we did not compute the Cj minus Zj. So 0 0 0, this is 0 0 0 0, so this will be minus 1 by 7 0, 5 by 7 plus 1 is 12 by 7, so I have a minus 12 by 7 0, 2 plus 17 by 7 is 31 by 7. Now we do one more iteration, again it is a dual simplex iteration, every Gomori cut results in a dual simplex iteration. So this goes, we need to find a theta. So minus 12 by 7 divided by minus 5 by 7 is 12 by 5, 1 by 7 is 1, so this variable enters, x3 enters again. So the next simplex iteration we will do it here. So we will have x1, x2, x3, x4, x5, x6 with x3 replacing x6. So x1, x2, x4, x3. So this is your pivot element. Divide by the pivot to get 0 0 1 0 5 minus 7 and 3 here. This minus 1 by 7 times this, or simply this plus this. This R1 minus 1 by 7 times this row is the same as simply adding this and this. So, you would get 1 0 0 1 by 7 minus 1 by 7 again 0 5 by 7 minus 5 by 7 0 0 plus 1 1 17 by 7 minus 3 by 7 is 14 by 7 which is 2. Now, this is all right, there is no problem here, there is already a 0. So, write it as it is 0 1 0 0 1 0 2. This plus 12 times this will give me a 0. So, I have 0 0 0, this plus 12 times this is still 1, minus 45 by 7 plus 12 times. So, minus 105 by 7 which is minus 15, this plus 12 times this is 12, 43 by 7 minus 36 by 7 is 1, and you have reached the optimum. Because it is a dual simplex iteration, you do not have to do the Cj minus Zj again, it is a dual simplex iteration. So, optimality condition will anyway be satisfied. The moment you get your right hand sides integer valued, you have reached the optimum. For the sake of completion, you would still have 1 1 coming in here, 1 1 coming in here, 0 0 0 0 minus 1 minus 1 4. Okay. So, you have the same optimal solution with with x 1 equal to x 2 equal to 2 and z equal to 4. Right. What are the other issues in the Gomori cutting plane algorithm? 1, every iteration whenever you have when you have a non optimal solution, when the LP optimum is non optimal to IP, then you need a Gomori cut, and every Gomori cut is going to result in an additional constraint and an additional variable. Therefore, the time taken per iteration is gradually going to increase because subsequent iterations are going to have more constraints. The other advantage perhaps is still you need to do an iteration, but you could think in terms of a sensitivity analysis type, because every Gomori cut is like adding a constraint, adding a binding constraint to an existing LP optimum. So, you can treat it like sensitivity analysis. Since the Gomori cut does not ensure that you have a constraint which is a bound. For example, a Gomori cut could become something like some a1 x1 plus a2 x2 less than or equal to b1 or greater than or equal to something. It does not become a bound on the variable. Therefore, unlike in branch and bound, you cannot do it, just impose an upper bounded simplex algorithm on it. You need to treat it like adding a constraint which is like sensitivity analysis, and then you proceed. Now, there are proofs that Gomori's cutting plane, this is called the Gomori's cutting plane algorithm, every cut is a Gomori cut. So, the Gomori cutting plane algorithm converges to the optimum if an optimum exists in a finite number of iterations, but there is no proof or there is no result saying or having an upper limit on the number of iterations. When such a thing, when such a similar thing for simplex is exponential, you do not expect a nice polynomial bound on the number of iterations for the Gomori algorithm, you do not. The only nice thing about the algorithm is that it will eventually converge, that is all. There is no backtracking, there is no fathoming, there is nothing. So, in terms of storage, it is again a peculiar thing. You might get into a situation where you, as far as storage is concerned, it may behave better than branch and bound. But as far as running time is concerned, depending on the problem, you may get into a situation where branch and bound is better, because time per iteration or time per node would remain more or less constant in a branch and bound, whereas time per iteration varies in a Gomori cutting plane algorithm. Next, there is absolutely no guarantee that choosing a variable that has the largest fractional coefficient would terminate faster. There is no guarantee, but both experience and a greedy approach to the problem would make us consistently choose that variable which has the largest fractional coefficient, done more for uniformity and consistency and not for anything else. But it's just like the most positive Cj minus Zj is accepted based on experimentation. This is also accepted based on experimentation. You normally try to create a Gomori cut for a variable that has the largest fractional coefficient. You could branch or you could use any other variable also to create a Gomori cut. Gomori cut is always characterized by a negative value on the right hand side. So, when you write your Gomori cut, you should have a negative value on the right hand side. If you do not get one, then you have made a mistake somewhere. Now, let us go back and do a couple of other things. Yeah.
How does this
How does the algorithm go towards an integer solution? We will do that now by mapping it on the graphical method. So, we will just draw the graph corresponding to the original problem, go back and see what we have seen. Two Gomori cuts, we will go back and see what the two Gomori cuts represent or how they are, and what is the difference between a branch and bound cut and a Gomori cut. So, let us draw the graph as it is here. I think we had something like 1, 0 here, and the other one turned out to be minus 1.4, which could be here. So, the first constraint was something like this. Second constraint is 7 by 15 on x2. So, this is somewhere here, and minus 7 by 12 on x1. So, this is somewhere here. So, we got something like this. Of course, with the corner point 28 by 9 and 133 by 45. Now, let us go to the first Gomori cut. I think we will remove, we will rub some of these. I think we will rub this. This is not needed now. Maybe even this. Yeah. What are the first Gomori cut? Yeah. In terms of x3, x4 and the right hand side, you can leave out the x5. 4 by 15, 7 by 45, 43 plus 7 by 45 x4 is greater than or equal to 43 by 45. Now, go back and write x3 here. x3 is 7 minus 7x1 plus 5x2. So, 4 by 15 into 7 minus 7x1 plus 5x2 plus 7 by 45 into 7 plus 12x1 minus 15x2 is greater than or equal to 43 by 45. So, multiply the first one, you would get, so this is 12 into 7 minus 7x1 plus 5x2 plus 7 into 7 plus 12x1 minus 15x2 is greater than or equal to 43, and very quickly simplifying you get 84 minus 84x1 plus 60x2 plus 49 plus 84x1 minus 105x2 greater than or equal to 43. The 84x1 gets cancelled. 84 plus, no, what did I do? Yeah, 84 plus 49, 133. 133 minus 43 is 90. So, greater than or equal to minus 90. I have 60 plus 45, 105. So, minus 45 x2 greater than or equal to 90 gives me x2 less than or equal to 2. In this case, it turns out that the first constraint is the same as the branch and bound constraint.
Choose only integer thing in that part.
Normally it won't happen, it need not happen. A Gomori cut need not finally result in this form like an upper bound or a lower bound. You could have the other one.
The entry for another basic variable is greater than 1 and not.
We will look at the next one and see what happens. So, what did we do here? We just added another constraint x2 less than or equal to 2 and brought down the feasible region here. Now, what is the next Gomori cut? The next Gomori cut turned out to be, again it turned out x1 less than or equal to 3, right. So, if we substitute, what was the Gomori cut? 1 by 7 x3 plus 5 by 7 x4 x5 becomes x1 less than or equal to 3, but once again it just happens again in our example that your Gomori cut is becoming a bound. Please remember that this may not be the best example to illustrate that, it may end up misleading you that Gomori cut is always a bound. It just does not happen. You could always have a Gomori cut for a 2 variable problem, a Gomori cut of the form a1 x1 plus a2 x2 less than or equal to b1. Could have done that. Now, what happens here is x1 less than or equal to 3 takes us here, right. I am sorry, this is here, and this becomes the optimum, which is 2 comma 2. Now, what actually happens in a normal Gomori cut is, it does not happen this way, this is perhaps not the correct example for it. It does not, it also removes areas as the branch and bound does, but what it does is, for example, if this is the optimum, you could get a Gomori cut which could behave like this, which could be like this. Instead of the first cut, you could get a Gomori cut which is like this. It need not result in cuts which are parallel or perpendicular to the x and y axis. You could get a cut like this. So, it kind of takes away areas from the feasible region, areas closer, it makes the present optimum infeasible, it removes areas, and then it progressively chips off areas, unlike the branch and bound which cuts branch and bound is more like a gelatin cut, it just cuts either horizontally or vertically. Gomori is like chipping it off, just chip off a certain portion of the area till progressively you keep chipping off the areas till the LP optimum is integer value. Both of them try to do the same thing, but branch and bound does it in a certain systematic way, Gomori does it in a different way. Gomori cut can simply result, this could be your first cut, maybe this could be your second cut, it could happen that way. It does not make there are times it can make drastic cuts as it happened in this case, but after some iterations you will realize that the Gomori cut progressively removes smaller and smaller area. If you work out on large problems which might be difficult to demonstrate in a class, you will realize that one of the disadvantages of the cutting plane algorithm is that as the number of iterations increases, you will see that it does remove a certain area as in 2 dimension in every iteration, but as the iterations increase, the extent of gain becomes less and less, and Gomori's algorithm takes a little more number of iterations. And if you start mapping it on the graphical, you will see that the area that is removed by the Gomori cut progressively becomes lesser and lesser, and that is very important. Now, in a branch and bound, what will happen is, when you make a cut, this can happen both in Gomori as well as in branch and bound. A variable that at present has an integer value, because of a cut in the next iteration can take a non-integer value, and that actually makes the whole thing interesting, because if you put a restriction that the moment a variable takes an integer value, it cannot take non-integer, it automatically leads you to a way of writing a bound on the number of iterations, and that does not happen in any of these. A variable that takes an integer value in a particular iteration in a subsequent iteration can take non-integer values both in the Gomory's cutting plane method as well as in the branch and bound method. So, this is how the Gomory's cutting plane algorithm actually works, and as I said, there are proofs that this algorithm converges or terminates at the optimum in a finite number of iterations. For large problems, you will realize that the Gomory cuts become weak in the sense they remove smaller and smaller areas. You will realize that you will realize that very quickly you are very close to the IP optimum. The gap between the present LP optimum and the IP optimum is very small, but in a single cut it is not able to get you the IP optimum. So, it takes you to another cut, and once again you make a cut, you are still in between. As you keep proceeding, the gap just narrows down, and finally it gives you the integer optimum. So, that is how the Gomory cutting plane algorithm works. Now, a branch and bound, it's kind of advantageous to use a branch and bound when you have a mixed integer programming problem, because the more continuous variables you have, the easier it is for a branch and bound algorithm. You need only to branch on those variables that have fractional values for the integer. You might be tempted to think on the same lines with the cutting plane. After all, at any iteration I have to remember the Gomory cutting plane algorithm that we have seen is meant for all integer. It is not directly meant for a mixed integer, because remember that every Gomory cut results in a slack variable which is also an integer variable. So, it's an all integer cutting plane algorithm is what we have seen. It's called, this comes under the category of cutting plane algorithms. Cutting plane algorithm, it's an all integer algorithm, and the Gomory cut is an all integer cut, it's for an integer algorithm. Now, there are Gomory cuts, modifications of Gomory cuts for mixed integer problems. Obviously, when you are working on a mixed integer problem and you have an optimum simplex iteration, you will not bother about that variable which can take a continuous value. But if an integer variable takes a continuous value, you can't create a Gomory cut like what we did. That cut is meant under the all integer assumption. There are some mixed integer cuts. Mixed integer cuts are slightly different from all integer cuts. You may find them, but we will not go to that detail. As far as this course goes, we will say that we can use the cutting plane algorithm for all integer, and we will use it. And for mixed integers, there are modifications to the Gomory cutting plane algorithm, but we would recommend using branch and bound if you were to solve a mixed integer problem, because branch and bound under the same algorithm and structure you can solve an all integer as well as a mixed integer. Whereas, if you want to adapt the Gomory's method for the mixed integer, then you have to change the way the Gomory cut is written. Branch and bound has some advantages when it comes to solving mixed integer. The branch and bound, and every node of a branch and bound tree, you only create an upper bounded variable. So, as I said earlier, the size does not increase with increase in the number of iterations. In general, for integer programming problems, branch and bound is preferred to the cutting plane, because branch and bound can handle both all integer and mixed integer under the same algorithm, whereas a cutting plane algorithm has to have different cuts for each of these. And branch and bound, somewhere the time taken per iteration is more or less fixed, because every cut results in a bound. One can always have situations where the cutting plane algorithm is faster than the branch and bound and so on. Cutting plane may be better in terms of memory, and branch and bound may be better in terms of time. So, depending on the problem, one needs to look at both, but as a general rule, branch and bound is used more widely than cutting plane, simply because of its ability to handle both all integer and mixed integer under the same algorithm. Now, let us look at another thing here. There are two more types of all integer algorithms that we will see here as part of our integer programming. Now, those are called, there is an all integer dual algorithm, and there is an all integer primal algorithm. So, we will have to see both these, the all integer dual algorithm as well as the all integer primal algorithm. But before we see that, we will try to represent the Gomori cut or the Gomori cutting plane algorithm in a slightly different format. So, we will get into another way of representing a simplex table which is slightly different from what we had been doing. So, look at it very carefully, we had seen already different ways of making the simplex table. The simplex table in its regular tabular form that we saw in the first course, and then we have seen the matrix form of the simplex using the E1, E2 matrices, and then in the column generation algorithm we saw one way of representing the simplex table, and then in the decomposition we saw another way of representing the simplex table. Now, we look at a third way of representing the simplex table. We will take the same example and we solve it. So, the example is maximize x1 plus x2 7x1 minus 5x2 less than equal to 7, 12x minus 12x1 plus 15x2 less than or equal to 7, x1 x2 greater than or equal to 0. So, let us take first the linear programming problem and solve it, and then we will look at the integer programming problem and solve it. We will create a much smaller table here. x3 and x4 are the slack variables to begin with, and they will become the basic variables. So, what we will do is we will have something called a column called x naught or right hand. We will have a column called x naught, we will then see what this column is, or we will have a row called x naught, and then you will have your x3 and x4 which are the current basic variables. And then you have a right hand side, and then you have a minus x1 and a minus x2, where x1 x2 represent the present non basic variables. Now, this plus x maximize x1 plus x2 would be written as 0 minus 1 minus 1. See, this standard format is for a minimization problem. Okay, this I am sorry, you can assume the standard format is for a maximization problem. So, I have x1 plus x2 here. I already have a minus x1 minus x2, so the coefficients get multiplied to give me a plus x1 and a plus x2. Now, this will be written as x3 is 7, the equation becomes x3 equal to 7 minus 7x1 plus 5x2. So, 7 minus 7x1 will become plus 7, and this will become a minus 5. 7, one second. Yes. So, x3, repeat, x3 is equal to 7 minus 7x1 plus 5x2. 7 is written as 7 here, minus 7x1 will become plus 7 because of the minus 1, and plus 5 will become minus because of the minus. So, x4 will become 7 minus 12 plus 15. Now, this is like writing, if you leave this out, this is like writing Zj minus Cj, or this is like writing the dual. Right now, the dual is infeasible here, primal is feasible. Again, this is like writing the dual as it is. We are used to a convention in the tabular form where we write Cj minus Zj, which is actually the negative of the dual. So, we say positive Cj minus Zj enters for optimality. If you can always interpret it as a negative of the dual. So, a positive Cj minus Zj implies a negative dual. A negative dual implies infeasibility, which is non-optimality. therefore it enters. So, this implies dual negative, primal positive. So, primal positive, dual negative, you will do a normal simplex iteration. When the primal is negative, you will do a dual simplex iteration. So, you look at that variable where the most negative dual will come in, which is like saying the most positive Cj minus Zj will enter. In this case, there is a tie, you can break the tie arbitrarily. So, you enter that one like this. So, the leaving variable is taken, there is only one leaving variable 7 by 7, here you cannot divide for theta, 7 by 7. So, this is the leaving variable. So, you get into this, x1 comes in, so I get a minus x3 here and minus x2 here, I have an x0, I have an x1, I have an x4. Now, I am going to introduce a few rules with which you can directly make the simplex iteration. Now, this is going to be your pivot. Rule 1, pivot always becomes 1 by pivot. So, this becomes 1 by 7. Rule 2, divide every element of the pivot row, every other element of the pivot row by the pivot. Pivot alone will become 1 by pivot. Divide every other element of the pivot row by the pivot. So, this becomes 1, this becomes minus 5 by 7. Divide every element of the pivot column other than the pivot, which anyway written, divide every other element by minus pivot. So, minus 1, this will become minus 1 by 7, this will become plus 12 by 7. Sorry, this becomes 1 by 7, this becomes 12 by 7. Now comes the next set of rules. The value here will be this minus, this is the pivot column, this is the pivot row. So, this minus this into this, 0 minus minus 1 into 1 plus 1, 7 minus minus 12 into 1, 19. Repeat, 0 minus minus 1 into 1 plus 1, 7 minus minus 12 into 1, 19. And we have to do this similarly, we will continue this in the next lecture.